one application that I'd like to show you is how to find the area of a triangle. So we all know it's 1/2 the base times the height. But what if you don't know the base? What if you don't know the height? But you have something, another information about the triangle. How do you find the area? So that's one application I want to show you. And then the other application I want to show you is something that we call the law of sines, which is a relationship in a triangle that the sides and the angles enjoy. Okay, there's a way to relate the sides and the angles of a triangle with each other. So I just want to show you this, and then I'm gonna stop. I might give you more information, but at least so you can see how you can use these ideas that you have learned to do some geometry. Okay. All right. Anyways, let's see this. So what's the goal here? Well, to find the area of a triangle, right? To find an alternative formula for the area of a triangle. In particular, what we want is the following. So in particular, we would like to what I would like to do is be able to answer the following question. So given a triangle, let's say that I give you a triangle here, okay, and you know this side is A, this side is B. You don't know anything else. You don't know the height. You don't know the third side. And let's say that you know this angle. Let's call it theta. Okay. So in particular, given this picture, we would like to find the area of the triangle. So in this situation, what we want is find the area of the triangle with the given information. In other words, if you know two sides and the angle in between, we would like a formula that allows you to calculate the area. That's what we're trying to look for with the given information. All right, so solution to the above question. Okay, so here's what we want to do. So we have a triangle. Okay, so just gonna draw any triangle here. Let me not draw it so that it looks isosceles, because it doesn't have to be. So let me just draw some triangle here. And this is true for any type of triangle. It's just I have to pick one to draw. Okay, just drawing something like this. And then this angle is gonna be theta, but what I'm gonna do is the following. I'm going to draw, of course, the height of this triangle corresponding to the angle theta, but instead of saying theta, I'm gonna put two angles here. So I'm gonna put the angle alpha, and then I'm gonna put here the angle beta. So from this picture, it's clear that alpha plus beta equals theta, right? Because all I did was I draw the height, and so this line splits the angle theta into two pieces. One piece is alpha, another piece is beta. They don't have to be, this is not necessarily the angle bisector, okay? This is just the height. So that means alpha and beta, they don't have to be equal to each other. All right, so now I just want you to look at this picture and realize that there are two triangles here, okay? So we have this yellow triangle, and then of course we have the other triangle, and they are both right triangles, okay? And we have a very nice way of calculating the area of a triangle, okay? So how do we find the area of a right triangle? We just multiply the two legs and divide them by 2, right? So I'm gonna call this piece here, let's call it x1, and then this other piece here, let's call it x2. So the area that we're looking for, the area for a triangle, is gonna be equal to A1 plus A2, the sum of the two areas of the two little triangles that we obtained. The area of the first triangle is equal to x1 times h over 2, because it's the product of the legs divided by 2, plus the second triangle is also a right triangle, so this is going to be x2 times h over 2. Everybody following this so far? Okay, Now, let's look at the yellow triangle and let's say something about H. Let's relate H and A. So, let's see. Do I want to do that? Yes, I want to do that. So, in the yellow triangle, we're going to say something about H and we're going to say something about X1. I don't want H, I don't want X1 in this formula. Remember, we're supposed to give an answer using only A's, B's, and theta. So theta is not clear where it's going to come from, but so far we can say something about A, and we can bring A and B into the picture. So looking at the yellow triangle, okay. So looking at the yellow triangle, I would like to say something about H, and I would like to say something about X1. So notice that to say something about H, we should use cosine, right? So cosine of alpha is going to be equal to adjacent over hypotenuse. So from here we get that H equals A times cosine of alpha. That's using the yellow triangle. And similarly, to say something about X1, we can use sine, which is opposite over hypotenuse. So X1 is A times the sine of alpha. So what do we get for the first formula? So we're going to have 1/2. Now X1 equals A times sine of alpha. And then H, let's see, I don't want to touch H yet. And there is a reason for that. Actually, yes, no, I don't want to touch H yet. Okay, now let's use the blue triangle. The blue triangle, what do we know about H? According to a blue triangle, we can use then cosine of beta, right? Cosine of beta is going to be equal to H over B. So that means that H, which is the same, equals B times cosine of beta. And then similarly, what can we say about X2? We can use sine. Sine of beta is X2 over B, so that X2 equals B times sine of beta. Now, here is what I'm going to do. For the H in the formula for the area of the yellow triangle, I'm going to actually use this value of H. It's the same H, so I can use whatever I want. So instead of using A times cosine, I'm going to use B times cosine of beta. Okay? So I'm going to borrow that from there. And then we have plus, now X2, so this is going to be 1/2. And then X2 is B times sine of beta. And then for the H in the second triangle, I'm going to go ahead and use this formula over here for H, which is A cosine of alpha. All right, so that's what we get. Now, at least we have A's and B's. We don't have H, we don't have X1 or X2. Now we just have to do something about alpha and beta and hopefully bring theta into the picture. But it should be clear what's going to happen now. I'm going to take common factor. Notice that the first term we have 1/2 AB. And the second term we also have 1/2 AB. If I factor that out, what's left? We're going to have sine of alpha, cosine of beta, plus sine of beta, cosine of alpha. And surprise, surprise, what comes to mind when you see this? You should realize that this is the sum formula for the sine. So this is going to be equal to 1/2 AB times the sine of alpha plus beta, because this is sine cos plus cos sine. So in other words, if you want, flip the cosine with the sine, and then you have cosine of alpha sine beta. That's the same thing. And alpha plus beta is nothing more than theta. So moral of the story, the area of a triangle, if you know two sides and the angle in between, is equal to 1/2 AB times the sine of the angle. Questions on how we obtain this formula? Questions? Okay, so as a quick application, we can actually find a very nice formula for the area of an equilateral triangle. Okay, so Let's do some application, and you need this. This may pop up in calculus 1. You will need to know the area of an equilateral triangle, and also in calc 2. So these kind of things are important. So find the area of an equilateral triangle. Remember, equilateral means that all the sides are the same. Of an equilateral triangle of side L. In other words, if you have a triangle, equilateral means that all the sides are the same. So this is L, L, and L. We would like to find the area of this. Now remember, one property of equilateral triangle is that, okay, the three sides are equal, but also the three angles are equal. And because the three angles are equal, how much do they measure? What's the measure of the interior angles of an equilateral triangle? They are all 60. Good. So everybody is 60 degrees. So now we can, easily apply what we just discussed to find the area. So what's the area? It's gonna be the product of two sides. In that case, it's gonna be L. So 1/2 L times L times the sine of 60. And what do you know about the sine of 60? This would be 1/2 L squared times square root of 3 over 2. So formula for the area of an equilateral triangle is square root of 3 over 4 times L squared. So if you know the length of the side, you know immediately the area. Okay, questions? Okay, perfect. All right, so that was one application that I just wanted you to know, so you have that nice little formula, and that, for example, we get this nicer formula for equilateral triangles for the area. So we did a little bit of geometry here, and then the other application that I wanted to do is the so-called law signs. So let me show you what that is. So the law signs, I guess we're going to write down, is just a way of relating the angles and the side of a given triangle, okay? And we're gonna play with it first, and then I'm gonna write down the theory. So here is what's going on. Let's say that we have a triangle. Again, this is true for any triangle. I'm just gonna draw something here so that we have something to work with. So we have a triangle, and then we have A, B, C, and let's say, it's customary that the angles that are opposite to the corresponding sides, we give them alpha corresponds to A because that's the Greek letter A, beta corresponds to B because that's the Greek letter B, and then gamma, we use it for C, okay? All right, naturally gamma is the letter C in Greek, that I don't know, but I know alpha is A and beta is B. Okay, anyways, these are usually the letters that we use, but it doesn't matter. You can use whatever is your favorite letter. Now, the goal is to relate A, B, and C with alpha, beta, and gamma. So goal, find a relationship among A, B, C, and alpha, beta, gamma. Okay, and this will allow you to solve for triangles. Like sometimes, two sides and one angle, and then with that information you can figure out the other side, or you can figure out another angle and stuff like that. Okay. All right. So let's see. What can we do here? So here is what we can do. I'm gonna drop a perpendicular right here. Okay. So this is a 90-degree angle, and the moment that I do this, then we can do the following. Let's see. There are two triangles that pops up. I'm gonna call this side, let's call it H. And then in the first triangle, the one on the left, the one that has the angle beta, we notice that H is common to both triangles, okay? So we can somehow relate beta and alpha in the following way. So using the first triangle, we see that sine of beta equals H over A, okay? So that means that H is going to be equal to A times sine of beta. But then using the second triangle, we get that sine of alpha equals H over B. So then we get that H is going to be equal to B times sine of alpha. So because H is the same, then it follows that A sine of beta equals B sine of alpha. Or another way of saying this is that if you do A over sine of alpha, that's the same thing as saying B over sine of beta. So we get this relationship. So if you do A over the sine of the angle that opposes A, that's the same thing as B over the sine of the angle that opposes B. Okay? Now, to bring gamma and C into the picture, we're going to play the same game. It's just that instead of drawing this H relative to C, for example, let's draw a height relative to B. So, well, this picture, let's see, how do I draw perpendicular? In this case, it's going to be outside, but it doesn't really matter where it is. But let's see, I'm going to try to use from alpha. So mind that this is a 90-degree angle. Okay, so then in this case, let's see. Yeah, this is more than 90. Okay, so yes. Okay, so I'm gonna call this one H prime. So this is another height that this triangle has. Let's see. Write it like this. So I'm gonna call this one H prime. Okay, so we have a very tiny triangle, the one on top, that has the angle gamma inside, and then we have another triangle that has beta completely inside. Okay, so hopefully you see the two triangles that I'm talking about. I just don't want to color the two things. Actually, it's probably be easier if I just want to use the same picture. Okay, so the triangle, looking at the triangle that has gamma, then we can say the following: sine of gamma is going to be equal to the opposite, which is, so let's see, that's 90 degrees. So beta is the hypotenuse. So sine of gamma is going to be opposite, which would be H prime divided by hypotenuse, which is B. So that means H prime equals B times sine of gamma. And then using the other triangle, we can say that sine of beta is going to be equal to, the hypotenuse now is C, opposite, which is still H prime over C this time. So we have that H prime is C times sine of beta. But H prime is the same for both of them. So from here it follows that B times sine of gamma equals C times sine of beta, or B over sine of beta equals C over sine of gamma. But we already knew that B over sine of beta is also A over sine of alpha. So we get the so-called law of sines. That says the following, that for any triangle, so in any triangle with size A, B, C, and corresponding angles. When I say corresponding, I mean the ones that are opposed to each other, okay? Alpha, beta, gamma, we have, so alpha opposes A, beta opposes B, gamma opposes C, as we have in the picture, okay? So we have that A over sine of alpha equals B over sine of beta, which equals C over sine of gamma, okay? So this right here is what we call the law of sines. Do you have any question with this relationship? That that came up so far? Again, it's just playing with the picture. And let me give you a bonus that usually is not in the books here in America. Not sure why, but I'm going to give you a bonus, which is actually the true law of sine. There is a hidden term here that is not showing up in the books. Of course, you have to work a little bit harder to see the hidden term. Let me just quickly show you what it is. Every time that you have a triangle, we can always draw a circle that's circumscribed in the triangle, so that it passes through the three vertices of the triangle. Now with this picture, let's say the center is somewhere in here, then let's consider the following angle. I'm gonna draw a diameter here, and then we're gonna go this way. So now notice that there are two inscribed angles. We have this one here. That angle is the same as this angle right here, okay? So for example, if we have a triangle ABC, and let's say that this was the angle beta, okay, because it was B, and then we had an angle beta, remember ABC, then this angle right here is also beta, because they both are inscribed on the same arc. So the measure is half the measure of the arc, as we discussed earlier, and therefore they're both going to be, they're going to have the same measure. But let us focus now on this new triangle that was created. Notice that this right here is the radius, and this is the radius of the circle. So using this triangle, what do we obtain? So this angle right here is 90 degrees by Thales theorem that we mentioned earlier, because it's inscribed on a chord. So what do we have? We are going to obtain from here that, let's see, the sides opposing, so B over sine of beta, using the law of sine that we have above, B over sine of beta is going to be equal to the sine opposes 90 degrees, which is 2 times R, divided by the sine of 90 degrees. But as you know, the sine of 90 degrees equals 1. So we get the B over sine of beta equals 2 times R, where R is the radius of the circumscribed circle. So that's the hidden term that for some reason is not showing up in any book that you can come across here. I don't know, the classical books that they have for trigonometry here, for school, they don't have this hidden term, not sure why. Anyways, so where R is the radius of the circumscribed circle, where R is the radius or the circumscribed circle to the triangle. So this is my gift to you. You can now, if you want, brag with your friends that if they think that they know the law of sines, then you can tell them you don't know the hidden secret. Now you know what it is. Okay. Anyways, I'm gonna stop here.